Hello everybody, good morning. Myself, Dr. Shubhankar Sen, an associate professor from the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the fifth lecture of Module 5 of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In the fourth lecture, we started with the numerical solution of Poisson equation of heat conduction in 2 dimensions. We used the Galerkin finite element method and also used the bilinear quadrilateral elements. In the fourth lecture, we have computed the element level matrices and vectors. In today's lecture or the fifth lecture, we shall perform the assembly of element level matrices and vectors as well as implementation of the essential boundary conditions, and then we shall solve the matrix equation system. For the two-dimensional Poisson equation of heat conduction using bilinear quadrilateral square elements, the element level matrix which we have calculated, this can be represented as, for the bilinear square element, Ke equals to K into 1 by 6 into 4 minus 1 minus 2 minus 1 minus 1 4 minus 1 minus 2 minus 2 minus 1 4 minus 1 minus 1 minus 2 minus 1 4. So this is a 4 by 4 square matrix. This is obtained using delta x equals to delta y. Therefore, when delta x equals to delta y, Ke is a constant or fixed matrix. If you look into the rows of the matrix, then it is clear that R1 plus R2 plus R3 plus R4 equals to 0. Therefore, the matrix Ke at element level is linearly dependent, and hence the element level matrix equation cannot be solved at element level itself. So this is first row of Ke, second row of Ke. So Ke is a singular matrix and hence is non-invertible. Let us go back to the previous expression where we calculated this Ke. So here the thermal conductivity term was missing. So this is Ke equals to K. This is K by 6. Now we construct the LM array once more to perform the assembly. So the LM array is given as E 1, 2, 3, 4, 5, 6, 7, 8, 9, A 1, 2, 3, 4, I 1, 1, 1, 1, NEE 1, 2, 3, and 4. Here we make the boxes for the LM array. for the first element, second element, third element, fourth element, fifth element, sixth element, seventh element, eighth element, and the ninth element. So this was our mesh. In this case, we had equation numbers at the interior nodes as 1, 2, 3, and 4. At the boundaries, these equation numbers are all 0. 0 and 0. So, for the first element, the global equation numbers are 0, 0, 1, 0. For the second element, these are 0, 0, 2, 1. For the third element, these are 0, 0, 2. For the fourth element, this is 0, 1, 3, 0. 0, 1, 3, 0. For the fifth element, this is 1, 2, 4, 3. For the sixth element, it is 2, 0, 0, 4. For the seventh element, it is 0, 3, 0, 0. For the eighth element, this is 3, 4, 0, 0. And finally, for the ninth element, these equation numbers are 4 and 0, 0. Now, let us construct the assembled matrix equation. First, we construct the assembled matrix capital K. The components are K11 through K44. This will be a 4 by 4 matrix with 4 global unknowns. So first term is K11. If we look into the LM array, this K11 will be written as K331 plus K442 plus K224 plus K115. So these are all diagonal terms. All the diagonal terms are constant. They are equals to 4k by 6. So therefore you can multiply it by 4. So we have 16k by 6. Next is K12. So K12, if we search per element, then it is K432 plus K125, K125, K43. K43 is minus K by 6, minus K by 6, and K125, this is also minus K by 6. So we get minus 2K by 6. Next we get K13. K13 equals to K234, K234. Then we have at fifth element K145 plus K145. K23 is minus K by 6, and K14, this is also minus K by 6. So this gives us minus 2K by 6. Now we are left with the last term in the first row of the global matrix. So this is K14. K14 equals to, let us scan element wise. This is present only in the fifth element. K135 equals to K135. K135 is minus 2 by 6. Minus 2 by 6. So this is same for all elements. The stiffness matrix is common for all elements from E equals to 1 to E equals to 9. Then only we are able to just directly put the values during assembly. Next is the second row of the assembled matrix. This is K21. Now, directly from the weak form, we know that this assembled matrix will also be a symmetric matrix similar to the element level matrix. This element level matrix Ke is also symmetric, but it is not a sparse matrix. So Ke is symmetric, banded, and diagonal dominant. These features we already discussed. We get these features in an elliptic partial differential equation. So K21, it must be equals to K12. This will be minus 2K by 6. Now K22, this is the diagonal term. So this is K332 plus K443 plus K225 plus K116. All of these are diagonal terms. So we get 4K by 6 4 times. So we have 16K by 6, where K is the thermal conductivity. Next we have K23. So K23, 2 and 3 are simultaneously present only in the fifth element. So it is K245. K245 equals to minus 2K by 6, and K24 equals to K235. 2 and 4 simultaneously, they are present in two elements, in elements 5 and 6. So K24 will be K235 plus K235 plus K146. Now K235, this is minus K by 6, and K146 is also minus K by 6. So we get it as minus 2K by 6. Next we go to the third row. K31 equals to K13. Now our K13 was minus 2K by 6. So this is minus 2K by 6. K32 equals to K23 by symmetry. K23 is also minus 2K by 6. So minus 2K by 6. K33. K33 is K334. K334 plus K445 plus K227 plus K118. So, like the previous diagonal terms, easily we see that this is 4K by 6 into 4 equals to 16K by 6. The next term is K34. K34, we can see that it is present in elements 5 and 8. For element 5, it is K435, K435 plus K128, K128, K435, it is minus K by 6, minus K by 6, and K128, this is also minus K by 6. So here we get minus 2K by 6. Now for the last row, K41 equals to K14 equals to minus 2K by 6. K42 equals to K24. K24 is minus 2K by 6 minus 2K by 6. K43 equals to K34 equals to minus 2K by 6, and K44, the last term, this is K335 plus K446 plus K228 plus K119. K119, all of them are same, and they are 4K by 6 into 4 equals to 16K by 6. Now, by looking into the entries of the assembled matrix, we see that except the diagonal terms KII, all the terms are negative and all the terms are also identical. The off-diagonal terms are minus 2K by 6. Now, the assembled matrix capital K, I write this symbol to distinguish from the thermal conductivity, is a 4 by 4 matrix given as K equals to K11, K12, K13, K14, K21, K22, K23, K24, K31, K32, K33, K34, K41, K42, K43, K44. So, if we put all these data here, we find that we are having 16K by 6 minus 2K by 6 minus 2K by 6 minus 2K by 6. Next row is minus 2K by 6, 16K by 6, minus 2K by 6, minus 2K by 6, minus 2K by 6, minus 2K by 6, 16K by 6, minus 2K by 6. Final row minus 2K by 6, minus 2K by 6, minus 2K by 6, 16K by 6. So, this is the assembled matrix for the given Poisson equation. We can represent this matrix in a compact form as K equals to, we can take 2K by 6 as common, then we can write it as 8 minus 1 minus 1 minus 1 minus 1 8 minus 1 minus 1 minus 1 minus 1 8 minus 1 minus 1 minus 1 minus 1 8 equals to K by 3 into 8 minus 1 minus 1 minus 1 minus 1 8 minus 1 minus 1 minus 1 minus 1 8 minus 1 minus 1 minus 1 minus 1 8. Now, this matrix, this is linearly independent and non-singular. This is a contrasting feature with respect to the element level matrix. This matrix is not sparse just because we are using only a very coarse mesh of 9 elements. So if we increase the number of elements, in that case, the sparsity will be very much evident. So the assembled matrix is linearly independent and hence is invertible, unlike the element level matrix Ke. So we have constructed the assembled matrix equation. Then we have this assembled matrix as a banded matrix. It is a symmetric matrix and obviously it is a diagonal matrix. So it preserves the features reflected by the element level matrix. Now we construct the global load vector and also implement the boundary conditions. So for this, we show the domain again here. So our temperatures were 0 degree centigrade, 250 degrees centigrade, 50 degrees centigrade and 150 degrees centigrade. Now these corners, they are common to two boundaries, and because of that at every point we have two different temperatures. Such situations give rise to corner singularity. So this can be easily handled. We can take the average value of adjacent temperatures and put that average data for the boundary condition data at these singular points. So with this point, the lower left corner, the temperature will be 150 degrees centigrade plus 250 degrees centigrade divided by 2. This temperature we can take as 200 degrees centigrade. Similarly, here we can take the temperature as 250 plus 50 by 2 degrees centigrade. So this is 150 degrees centigrade at the bottom right corner. At the top right corner, the temperature will be 25 degrees centigrade, and at the top left corner, it will be 75 degree centigrade. Now, in the mesh, we have the equation numbers again. This is required again and again for implementing the boundary conditions and for performing the assembly. The equation numbers are 1, 2, 3 and 4. So element 1, element 2, element 3, element 4, element 5, element 6, element 7, element 8 and element 9. At the boundaries we know the temperatures, and we have already assigned 0 equation numbers at these essential boundary points. Now if we construct the load vector will have two components, one component from the source term and other component from the essential boundary condition. The load vector F, this is the global load vector, equals to contributed by the source term, contributed by source term, and this portion will be contributed by EBCs. Now this global load vector, this is a 4 by 1 vector. All of them are 4 by 1 vector. So let us first consider the portion contributed by the source term. So F source equals to F1 source, F2 source, F3 source and F4 source, 4 by 1, 4 by 1. This is source part. So this is, if we look into this, we can see that by observation also we can make the assembly. So F1 equals to F31 plus F42 plus F23 plus F14 5. Now when we go for the F2, then we see here F3 2 plus F4 3 plus F2 5 plus F1 6. If we observe these first two rows, then we understand that here in the source term load contribution, we are having contribution from local nodes 3, local node 4, local node 2 and local node 1. Similarly, for the third portion, we can write it as F33 plus F4 5 plus F2 7 plus F1 8, and finally for the fourth contribution we have F3 5 plus F4 6 plus F2 8 plus F1 9. Now we have already seen that the load vector contribution FIE, it was Q into del X del Y by 4. So all these contributions are same for I equals to 1 to 4. This gives us, for all elements, we have the same contribution from the source term, and that is given by Q delta X delta Y by 4. So we can write it as Q into delta X delta Y by 4 into 4, Q into delta X delta Y by 4 into 4, Q into delta X delta Y by 4 into 4, and finally Q into delta X delta Y by 4 into 4. So this becomes Q into del X del Y 1 1 1 1. This is 4 by 1 vector. So this is the contribution from the source term. Now let us consider the contributions from the EBCs to the global load vector. We make the problem definition again here. So this is 0 degree centigrade, this is 50 degree centigrade, this is 250 degree centigrade, this is 150 degree centigrade, this is 25 degree centigrade, this is 150 degree centigrade, this is 200 degree centigrade, and this is 75 degree centigrade. So here we have our elements. So element 1, 2, 3, 4, 5, 6, 7, 8, 9. Now here our equation numbers are like 1, 2, 3, 4, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, element 1, element 2, element 3, element 4, element 5, element 6, element 7, element 8, and element 9. We got the element level matrix, it was KE was K by 6, 4, minus 1, minus 2, minus 1, minus 1, 4, minus 1, minus 2, minus 2, minus 1, 4, minus 1, minus 1, minus 2, minus 1 and 4. So this was a 4 by 4 matrix. Then our LM array was E 1, 2, 3, 4, 5, 6, 7, 8, 9. A was varying from 1, 2, 3, 4. I was 1, 1, 1, 1, and N, E, E, it was 1, 2, 3, and 4. So now we can fill in the boxes in the LM array. So these are for our element 1. For element 1, the numbers were 0, 0, 1, 0, 0, 0, 1, 0. For element 2, 0, 0, 2, 1. For element 3, 0, 0, 0, 2. For element 4, 0, 1, 3, 0. For element 5, 1, 2, 4, 3. 1, 2, 4, 3. For element 6, 2, 0, 0, 4. 2, 0, 0, 4. For element 7, 0, 3, 0, 0. For element 8, 3, 4, 0, 0. For element 9, 4, 0, 0. Now, the contribution from the EBC, it is given as FIE equals to FIE source minus summation of KIJE TJE, where J belongs to eta G, I unknown local node. Now let us consider the contribution from the first equation. So here our global load vector F equals to F1, F2, F3, F4 equals to F source plus F due to EBC. So let us first construct the F1 term. F1 equals to F1 due to source minus summation. Now this equation number 1, it is common to elements 1, 2, 4 and 5, but element 5 is an internal element, so element 5 will not contribute to the essential boundary condition part. Contribution from the essential boundary will come from elements 1, 2 and 4. Let us first consider element 1. So for element 1, our I is local node 3 because we write the equation at local node 3. So this is K 3B1 TB1. This is for E equals to 1. B belongs to eta G. Now for element 2, it will be K. For element 2, the contribution comes from the nodes 1 and 2 for the essential boundary, and we write the equation at local node 4. So I equals to 4. So K 4B2 TB2 minus, now The next element is the fourth element. So here we write the equation at local node 2. So I equals to 2. So minus k 2b4 tb4. So this gives us F1 source. It was q into delta x into delta y minus k. Our b, it is 1, 2 and 4 for the first element. So it will be 311 T11 minus K 321 T21 minus K 341 T41. This is contributed by E equals to 1. These local nodes 1, local node 2 and local node 4, they are at the boundary, or they are the small b things. Okay, so for E equals to 1, B equals to 1, 2 and 4. Here I equals to 3. So this gives us the contribution from the first element. Now we have contribution from the second element. For this case, we have the equation written at local node 4. So I equals to 4 minus K 412 T12 minus K 422 T22. This is contributed by E equals to 2, and final contribution comes from E equals to 4. Here I equals to 2. So here we first write minus K 214 T14 minus K 244 T44. So this is contributed by the fourth element, E equals to 4. So if we substitute the values here, we can find that F1 equals to Q into delta x delta y minus our K311. K311, it is minus 2k by 6. So we get here minus 2k by 6 into T11. T11 is 200 degrees centigrade. It gives us 200 minus K321 T21. 32 is minus k by 6. So this is minus k by 6 into T21. So T21 is 250 degrees centigrade into 250 minus K341. K34 is minus k by 6. Minus k by 6 into T41. So for the first element T4, it comes on the left boundary. So this is 150 degrees centigrade. Next term is for the second element K412. K41, this is minus k by 6. So this is minus k by 6 into T12. So for the second element, the first local node, this is having 250 degrees centigrade temperature. So this is into 250. The next term is K422 T22. K422, it is minus 2k by 6. Minus 2k by 6 into T22. T22 is also 250 degrees centigrade. So now we are left with the last term minus K214 T14. K214 is minus k by 6. So this is minus k by 6 minus k by 6 into T14. For the fourth element T1 is 150 degrees centigrade into 150 minus K244. K244 is minus 2k by 6 minus 2k by 6 into 150. So here we put q into delta x equals to 0.5 equals to delta y. Delta x equals to delta y equals to 0.5 q into 0.5 whole square plus we see that k by 6 is present in all of the terms and each of the term is positive. So we can take k by 6 outside. So this is k by 6. Then we can get here 2 into 200 plus 250 plus 150 plus 250 plus 2 into 250 plus 150 plus 2 into 150. So this is plus 2 into 200 plus 250 plus 150 plus 250 plus 2 into 250 plus 150 plus 2 into 150. So we can see that this is q into 0.25 plus k by 6 into this is 400, this is 400, this is 500, 750 and 150 is 900 plus 300. So this is 0.25q plus 4 and 4, 8, 17, 2000. So it is 2000 k by 6. Now putting q equals to 1 watt per meter cube and k equals to 1 watt per meter degree centigrade, this gives us F1 equals to 0.25 plus 1000 by 3. So this is 0.25 plus 333.33. This is 333.58. So we have constructed the first row of the global load vector. Similarly, we can calculate F2, F3 and F4. So let us do it. Now to calculate F2, we need the mesh picture again and we also need the element level matrix. So Ke equals to k by 6, 4 minus 1, minus 2 minus 1, minus 1, 4, minus 1, 2, minus 2, minus 1, 4, minus 1, minus 1, minus 2, minus 1, 4. And then our mesh picture is like 1, 2, 3, 4. These are the global equation numbers 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0 and 0. Element 1, element 2, element 3, element 4, element 5, element 6, element 7, element 8 and finally element 9. So our F2 will be F2 source minus this F2, this is this particular equation, this will be contributed by elements 2, 3 and 6. So let us consider element 2 first. for element 2, we are writing the equation at local node 3. So our I will be 3, E will be 2, and B will be 1 and 2. So we have minus K 3 1 2 T 1 2 minus K 3 2 2 T 2 2. So this is the contribution from element 2. The next contribution will come from element 3. So here we write the equation at local node 4. So our I will be 4 and B will be 1, 2 and 3 and E will be 3. So we write here minus K 4 1 3 T1 3 minus K 4 2 3 T2 3 minus K 4 3 3 T3 3. And finally we have contribution from the sixth element. So this is from the third element, E equals to 3. For the sixth element, the contribution will come from local nodes 2 and 3. We write the equation at local node 1. So I is 1, E is 6 and B is 2 and 3. So this is K 1 2 6 T2 6 minus K 1 3 6 T3 6. So this gives us F2 equals to F2 source. We already know that it is 0.25 Q. By putting the value of Q as 1, this was 0.25. Now K312, K31 is minus 2. So this comes as minus 2K by 6 into T12. For the second element, first local node, the temperature was 250 degrees centigrade. So this is 250. So here we show the temperatures again. This is 0 degree centigrade, 50 degrees centigrade, 250 degrees centigrade, 150 degrees centigrade, 25 degrees centigrade, 150 degrees centigrade, 200 degrees centigrade, and here it was 75 degrees centigrade. So next term was K322. K322 is minus K by 6. So this is minus K by 6 into T22. So T22, this is also 250 degrees centigrade. It is 250. Next we go for element 3. It is minus K413 T13. K413 is minus K by 6. Minus K by 6 into T13. For the third element, the first local node, the temperature is here 250 degrees centigrade. Next we have K423 T23. K42 is minus 2K by 6 minus 2K by 6 into T23. So T23 is the lower right corner. This is T23. This temperature is taken as average temperature of 150 degrees centigrade. The final term from element 3, it is K433 T33. So K433, it was minus K by 6 minus K by 6 into T33. T33 comes on the right boundary where the temperature is 50 degrees centigrade. Here we have contribution left from the sixth element. So we calculate it as minus K126. K12 is minus K by 6 minus K by 6 into T26. For the sixth element, it is at the right boundary. The temperature at the right boundary is 50 degrees centigrade. So T26 is 50 degrees centigrade. The last term is minus K136. K13 is minus 2K by 6 minus 2K by 6 into T36. T36 is also 50 degrees centigrade. So it is 50. Now let us connect all the terms. We can see that all the terms are positive and all the terms in the EBC contribution, they have a common term of K by 6. So we simplify it as 0.25 plus K by 6, 2 into 250 plus 250 plus 250 plus 2 into 150 plus 50 plus 50 plus 50. So let us make a cross check. This is 2 into 250 plus 250 plus 250 plus 2 into 150 plus 50 plus 50 plus 2 into 50. So this term will be 2 into 50. So this gives us 0.25 plus K by 6 into, this is 500 plus 500, this is 1000, this is 300 and 100 is 400, 300 plus 100 400 plus 100 500. So this is equals to 0.25 plus K is 1, so it is 1 by 6 into 1500. So this is 0.25 plus 250, this is 250.25. Similarly, we can calculate F3 and F4. If we go for F3, then we get it as 0.25 minus F3 is this particular equation. It will be contributed by elements 4, 7 and 8. Let us consider element 4 first. So here for element 4, we are writing the local equation at I equals to 3. So our I equals to 3, our B will be 1 and 4 and E will be 4. So it will be K 3, 1, 4 T14 minus K 344 T44, because here I is 3, our B's are 1 and 4 and E is 4. So this is contribution from E equals to 4. Next we have contribution from element 7. We write the equation at I equals to 2 and our B values are 1, 3 and 4. So it will be K 217 T17 minus K 237 T37 minus K 247 T47. This is for E equals to 7 and final contribution comes from E equals to 8. Now for E equals to 8, we write the equation at local node 1. So I equals to 1 and B equals to 3 and 4, E equals to 8. So we get K 138 T38 minus K 148 T48. These are for E equals to 8. So for 8th element, our I was 1 and B were 3 and 4. So we can write it as 0.25 minus K31, it is minus 2K by 6, minus 2K by 6. Now T14, for the 4th element, first local node, it lies on the left wall. So temperature is 150 degrees centigrade. K344 T44. K344, it is minus K by 6. So this is minus K by 6 into T44. T44 also rests on the left wall. So this is 150 degrees centigrade minus K217. K21 is minus K by 6 minus K by 6 into T17. T17 for the seventh element, first local node lies on the left wall. This temperature is also 150 degrees centigrade. Next is K237, T37. K237, it is minus K by 6 minus K by 6 into T37. So for the seventh element, third local node, it is on the top wall where the temperature is 0. It is minus, it is into 0. Next is minus K247. 24, it is giving us minus 2K by 6 minus 2K by 6 into T47. T47, it is on the top left corner. T47's temperature is 75 degrees centigrade into 75. Then we are left with the eighth element K138. K13 is minus 2K by 6 minus 2K by 6 into T38. For the eighth element T3, it is 0. So this is 0 minus K148. K14 is minus K by 6 minus K by 6 into T48. For the eighth element, the temperature is 0 at the fourth local node at the top wall. So this is also 0. So we can simplify this as 0.25 plus K by 6 into 2 into 150 plus 150 plus 150 plus 2 into 75. This term is 0. This is 0. This is also 0. So we are left with 2 into 150 plus 150 plus 150 plus 2 into 75 means 150. So this gives us, after putting K equals to 1, 0.25 plus 1/6 of 300 plus 300 plus 150. So this is 0.25 plus 750 by 6. 750 by 6 is 125. So this is 125.25. Now we are having the last term, the F4 term. F4 equals to 0.25 minus, for the F4, this is the location. So we have contribution from elements 6, 8 and 9. So let us first consider element 6. For element 6, I equals to 4 and B equals to 2 and 3. So minus K426 T26 minus K436 T36. This is contribution from the sixth element K426 T26 minus K436 T36. Next, this is from E equals to 6. Next contribution will come from E equals to 8. So here I equals to 2 and B equals to 3 and 4 and E equals to 8. So minus K 238 T38 minus K 248 T48. This is contributed by E equals to 8 and final contribution comes from E equals to 9, for which I equals to 1 and B equals to 2, 3 and 4 and E equals to 9. So K 1 2 9 T2 9 minus K 1 3 9 T3 9 minus K 1 4 9 T4 9. This gives us 0.25 minus, now K42, this is minus 2K by 6 minus 2K by 6 into, this is for E equals to 9, T2 6. Now for the sixth element T2, it falls on the right boundary where the temperature is 50 degrees centigrade minus K436. K43 is minus K by 6 minus K by 6 into T36. So for the sixth element, third node, it also falls on the right boundary. Here the temperature is 50 degrees centigrade minus K238. K23 is minus K by 6 minus K by 6 into T38. On the eighth element, we have at the top surface temperature is 0. So it is 0 minus K248. K248 is minus 2K by 6 minus 2K by 6 into T48. T48 is also 0 degree centigrade, so this is 0. Now coming to the ninth element, we have K129, it is minus K by 6 minus K by 6 into T29. T29, it falls on the right boundary where the temperature is 50 degrees centigrade minus K139 T39. K13 is minus 2K by 6 minus 2K by 6 into T39. T39 is the top right corner where the temperature is 25 degrees centigrade minus K149. 149 is minus K by 6. So this is minus K by 6 into T49. So T49, it falls on the top surface with temperature specified as 0 degree centigrade. So this gives us 0. Now we can simplify this term as 0.25 plus K by 6 into 50 into 2. So this is K by 6, 50 into 2 plus, here it is 50, this is 0, this is 0, here it is 50, here it is 2 into 25, 2 into 25, the final part is 0. So we are left with 0.25, K equals to 1 by 6 into 100 plus 100 plus 50. So this is 0.25 plus 250 by 6 equals to 0.25 plus 125 by 3 equals to 0.25 plus 41.67. So this is 41.66, so it is 41.67. So we can write it as 7 and 5 to 9. So 41.92. Now we can construct the global matrix equation system. The global matrix equation system is constructed as KT equals to F, or K is 1 by 3, 8, minus 1, minus 1, minus 1, minus 1, 8, minus 1, minus 1, minus 1, minus 1, 8, minus 1, minus 1, minus 1, minus 1, 8. So this is 4 by 4. T1, T2, T3, T4 equals to, let us check these numbers. It was, the first value was 333.58, 333.58. The next was 250.25, 250.25. The next was 125.25, 125.25, and the final was 41.92. 41.92. We show the mesh here again. So this is T1, this is T2, this is T3, and this is T4. So using direct or iterative solver, find the unknown vector T1, T2, T3, and T4. Here I conclude today's class. In today's class, we have illustrated the computations for global stiffness matrix and global load vector. For generation of global load vector, we performed implementation of essential boundary conditions. The global matrix K is linearly independent, symmetric, banded, and diagonal dominant. For today's class, I suggest the textbooks by Professor Hughes and Professor Reddy. Thank you very much for attending today's lecture.